we're going to talk about something called the row echelon form of a matrix, and later we're going to talk about something called the reduced row echelon form of a matrix. So to start off, a matrix is in row echelon form, which I'm going to abbreviate as REF, if it satisfies two properties. The first property is that all rows of 0, so a row in the matrix that just consists of zeros, are at the bottom of the matrix. The second property is that the leading coefficient of every non-zero row is equal to 1 and always to the right of the leading coefficient of the row above it. And I'll show you what I mean in just a second. So for example, let's say we have this 4x4 matrix where these stars just represent any number. This is in row echelon form. Let's see. So we don't have any non-zero rows, so we don't have to worry about the first property here. The second property says that the leading coefficient, so that's the first entry in your row, in a non-zero row, so it is equal to 1. So you can see that for each one of these rows, the first number, the leading coefficient, is equal to 1, and always to the right of the leading coefficient of the row above it. So there are no rows above this one, so we don't have to worry. Here, you can see that this one is to the right of this one. And then this one is to the right of the one above it, and so on. Why this is called row echelon form is because you get something that's like a staircase. You can see. And that's what you want to think of when you're looking at these types of matrices. Here's another example of something in row echelon form. Again, this is going to be a 4x4 matrix. So it's going to have 4 rows and 4 columns. Okay, first thing to notice is that the 0 rows are at the bottom of the matrix. I have 2 0 rows and they're below any non-zero rows. Also, the leading coefficient of the first 2 rows is a 1, which is great, and this one, which is in the second row, is to the right of the first one. So we get a little staircase like so. I'm going to do one more. So this will also be a 4x4 matrix. This is a matrix in row echelon form. Here is the staircase. You can see that 0 rows, we only have 1 and it's at the bottom, and the leading coefficient of each row is a 1, and this one is to the right of this one. And this leading one is to the right of this one. It's over 2, but it's still to the right, so it satisfies the second condition. Okay, let's look at some real examples where these are not just stars. Let's see, is this matrix in row echelon form? The answer is yes. You can see that all of these have a 1 as a leading coefficient, and each one is to the right of the one before it. Okay? Is this matrix in row echelon form? The answer is yes. Here are two 0 rows, they're at the bottom, leading ones, and this one is to the right of that one. Okay. This matrix is in row echelon form. You can see that it satisfies our two properties. What about this matrix? So before we were looking at 4x4 matrices. Now that we have something called a 3x2 matrix, I have 3 rows and 2 columns. Is this in row echelon form? The answer is yes. The leading coefficient of this row is a 1, and the non-zero rows are below it. So this is in row echelon form. How about this one? This is a 2x4 matrix. This is also in row echelon form. That has a 0 row, it's at the bottom of the matrix. And you can see that for this row, the first non-zero number is a 1, which is exactly what we need for row echelon form. Let's move on. Let's talk about something called reduced row echelon form. So reduced row echelon form is very similar to the row echelon form. It's called reduced row echelon form because it's one extra step. So number 1, a matrix is in reduced row echelon form if it's in row echelon form and each column that contains a pivot, this is a new word here, but that just means the leading coefficient. So each column that contains a pivot has zeros everywhere else in the column. Specifically above it. That's something I want to mention to you as well. If you look back at this row echelon form in our definition, notice that whenever we had a leading 1, below the leading 1 we always had zeros. So you can see that in this example, this one, so all of our examples, because remember that the next leading 1 was always to the right, that would force the ones underneath the leading ones to be 0. The difference between row echelon form and reduced row echelon form is that wherever we have a leading 1, we're also going to zero out anything that's above that leading 1. So here we have zeros below, but we don't have zeros above, and we're going to do that. So for example, these two matrices are in reduced row echelon form. First, they're in row echelon form, because look at this one. We have a 0 row at the bottom, and then we have a leading 1 here and a leading 1 here, and this leading 1 is to the right of this one. But also, this column here has only zeros and a 1. There's nothing else in this column, and same thing here. So that satisfies the second condition. Each column that contains a pivot, which is this leading 1, has zeros everywhere else in the column. Let's look at this example here. This is a 3x5 matrix. It has no zero rows, and we can see that the leading 1 is here. So this is a pivot, this is a pivot, and this is a pivot. The pivot here is to the right of this one, the pivot here is to the right of this one. There's zeros below, like I was talking about, but notice also that we have zeros above these ones. So we have to make sure that the only thing in a column with a leading coefficient A pivot is just this 1 and there's nothing else. Okay? If I put something else here, like if I put, let's say a 6 and a 3, this would not be in reduced row echelon form because we would have to have zeros here, but it is in row echelon form because it satisfies the properties of row echelon form. Okay? So how will this help us with what we've done so far, talking about linear equations, systems of linear equations? Now look at this example here. You should have seen it before. We talked about it in the last video. We wanted to solve this system. And how we solved it is we found an equivalent system. And the equivalent system, I'm not going to rewrite it, but what I am going to do is I'm going to give you the matrix that gave us the equivalent system. So from here you can build the equivalent system. Let me just do that. So we get x1 plus 1/2, x2 plus 3/2, x3 is 1/2, x2 minus x3 is -1, and x3 is equal to 2. This matrix that we used earlier, this is in row echelon form. That's because you can see that here is a leading coefficient, here's a leading coefficient, right here, and this is a leading coefficient. And notice that these leading coefficients, they're to the right of the leading coefficient of the row above it. So it does follow row echelon form. It's not a matrix in reduced row echelon form because you see right here and here, we get something that's not 0 in these places here. Okay, so what we did was we took a system, we found the augmented matrix. Remember, we used that word, augmented matrix, which was taking the coefficient matrix of the system and then putting these solutions here with a line. You can ignore this line, you can just delete it if you want, but this line just keeps us keeps everything straight, letting us know that these are the solutions and these are the coefficients. And when we get something in row echelon form, we get a nice system like this. And this system, we were able to take this x sub 3 and plug it into the last one, find x sub 2, and so on. So we were able to solve this pretty fast. Now let's get this same matrix into reduced row echelon form. So I am going to get rid of this 1/2, this -1, and this 3/2. That way, we're going to get something that will also be an equivalent system to this, but it'll look even nicer than this system here. Okay, so let me show you how I'm going to put this into reduced row echelon form. So let's erase this. And let's see what I can do. What I want to get rid of is this 1/2. How can I get rid of this 1/2? Well, remember that when we want to change a system, we use elementary row operations. And the elementary row operations can be moving rows, like alternating them. We can multiply by a non-zero number, and we can add one row to another. So what I'm going to do, notice if I multiply this by a -1/2, I can add it to here and get rid of this number. But I'm also going to have to multiply everything else by a -1/2 and add it to the top. So I'm going to take -1/2 times it by row 2 and then add that to row 1. Okay, so I'm going to leave row 2 alone. And I'm going to multiply this row by -1/2. So some people put it down here. Let's do that. Maybe that'll keep us straight here. So 0, -1/2. This would be 1/2, and then 1/2. And then add all of these to this top row. So we get 1, 0, 3/2 plus 1/2 is 4/2. So 4/2 is 2. And then 1/2 plus 1/2 is 1. Okay, so we zeroed out this. Now we want to get rid of these two. So what I'm going to do is I'm going to take row 3, and I'm just going to add it to row 2 because that'll get rid of this -1. And then after that, I'm going to multiply row 3 by -2 and add it to row 1. Okay, so we're going to take row 3 and add it to row 2. I'm going to do this in 2 steps. Oops. Okay, so if I add it, I'll get 0, 1, 0, 1, right? Okay, and then I'm going to take -2 times row 3 and add it to row 1. So it's going to leave row 2. Oops. It's going to leave row 2 alone. And row 3 alone, but if I multiply this row by a -2, I get 0, 0, -2, -4, and this top row will be 1, 0, 0, -3. -3, 1, 2. So what does this simplify to? We get the linear system. I'm going to erase this so I have some room. x1 plus 0x2 plus 0x3 is -3. 0x1 plus x2 plus 0x3 is 1. And then the last row is just x3 is equal to 2. So what you see is x1 is -3, x2 is equal to 1, and x3 is equal to 2. And this was actually the solution to our system, to this original system here. So we found an equivalent linear system, and this equivalent linear system gave us the solutions to this. So row echelon form, which is what we have right here, is what we did in the previous video. That's really nice. It was able to help us find the solution, but we still had to use back substitution. We had to plug in x3 to figure out what x2 was and so on to get our solution. But if we put the matrix into reduced row echelon form, then we get something like this. As you can see, this one here, which gives us the solution automatically. So reduced row echelon form is the best form of this augmented matrix to give us the solutions to a linear system. And we're going to be using reduced row echelon form a lot in this class.